And go back a page. Hello out there. So Stanton, my apologies. Like the other day, I forgot to start recording. So we are looking at numerical integration, starting off with Riemann sums as a review. And so here I'm trying to find the area under the curve x squared plus 5 with right-hand endpoints on the interval from 5 to 7. So it's always a good idea to sketch the situation. We always have to calculate the width of our interval and then break that width into little chunks. And usually we go for uniform chunks, like the right-hand endpoint, upper sum, lower sum, left-hand endpoint. We also had that midpoint rule. Width of each interval is a half here. So then I just have to calculate the heights. Zooming in on my number line, if n equals 4, I'm going to go to 5.5, 6, 6.5, and 7. And so I need to calculate each of those y values and then multiply all of them by a half to get each rectangle's area. So now I'm going to try that on my calculator, and I think I'll go for my regular one. So I'm going to have 1/2 times parentheses 5 1/2 squared plus 5 plus 6. Yeah, it's just 6, right? It's the next one. 6 squared plus 5 plus 6 1/2 squared plus 5 plus 7 squared plus 5. Oops. 5, close parentheses, and my rough estimate of the area with right-hand endpoints is 88.75. I typed it right. We got confirmation on that from a couple people. And this is an overestimate because my function was increasing. So I have these little funky, not quite triangle shapes, parabola type triangles that I'm over each time. If I did left-hand endpoints, that would be an underestimate, and then I could average the two of them to get closer to the middle. Okay, so we're going to take a slightly different approach, and averaging them is kind of like finding the midpoints where you balance. And so that was another thing we did before. So I'm going to bring up a new way to do it. So again, we have some curve, and we need more color. So zooming, where's my color? Come on, there you are. Zooming in on one of those chunks, that's my distance h, or delta x right there. Okay. And we went for the right-hand endpoint, which was an overestimate. You could go for the midpoints, and the midpoint kind of splits the error. It's a little over on one side, a little under on the other side. And depending on the steepness of the curve, it could be an overestimate or an underestimate. Okay, and so it's hard to say until you actually do it to figure out like which triangle is bigger. Another way to do this would be, so let's redraw curve, function, values, a width of h. What we could do instead is pick the right point and the left point and then connect them with a straight line. Okay. Now, the straight line and the curve aren't going to match exactly. In this case, my line is above the curve. It's kind of hard to see because I didn't draw that very well. Try that again. All right, so maybe that's my straight line right there. So here, because it's concave up, I'm going to have a slight overestimate. If it were concave down, like that, and I connected the two endpoints, then in this case, I would have a slight underestimate. Question, what kind of shape do I have drawn there? That is a trapezoid. It's got a pair of parallel lines here and here. Doesn't matter what the other two sides are doing. So I can use what's called the trapezoidal rule instead. Trapezoid is pretty straightforward in terms of calculating Now here we use h for like our delta x, the little width of our interval. That's a nice letter to pick because if we take this trapezoid and just lay it sideways like that, so my trapezoid looks something like that, these two lines are parallel to each other. This could be called the height of my trapezoid. The base over here, I could say that's x sub k plus 1, and then this would be x sub k on the other side. So this height on that side would be f of x sub k plus 1, and on that side the height would be f of x sub k. So looking at my trapezoid sideways here, my longer base at the bottom, it's longer only because the function's increasing, is f of whatever the k plus 1th x value is. And then this one would be f of x sub k. And because this is a linear segment on the right side and the left side, I can use an average base of the top and the bottom. So what I can say is the area of a trapezoid, didn't come up very well, is equal to the height times the average of the two bases that are parallel to each other. So f of x sub k is one base, f of x sub k plus 1 is the other. And so that's the area of any one of these trapezoids. So cleaning that up a little bit, I'm adding a whole bunch of these trapezoids up. Each one has an area of h over 2 times the function value at the left endpoint plus the function value at the right endpoint. So what I end up with is a kind of weighted average going on there. It's exactly weighted average. And then I want to sum all of these guys up. Where does the sum go from and to? That can be a little tricky. Let's see. Usually we say we start at some x value called a and another one called b. And usually we want n subintervals. I like to call the first one, that would be x sub 0. So the first one after that is x sub 1. And then there's an x sub 2. Somewhere in the middle is that x sub k, my counter. And then all the way down to the end, the last one here, b, is actually x sub n, and right next to it would be x sub n minus 1. So that's what my subinterval looks like. In the previous example, we had n equal to 4. So I would have 1, 2, 3, 4, puts me at the end there. Okay. And that gives me n chunks that are all supposed to be the same size here. The width of each of those we usually call h. Sometimes we call it delta x. And remember, h is always the width of the interval b minus a divided by how many chunks you made, n. So that's this number h up here, the width of each subinterval. So according to the way I drew my number line out with all my little x values to partition it, then I would be taking the sum as k goes from 1 all the way to n. Is that true? No. If I let k go from 1 to n, then this would be 1, 2, and at the end it would be n and n plus 1, which takes me outside of my interval. So I usually don't like to start k at 0. I'm going to change these subscripts here. Instead of, I need two numbers next to each other like k and k plus 1, but I need to back up a step if I want to end this at n. Oops. Because notice right now, if I plug in n for k, that takes me to k plus 1, which is outside of the range, the domain I should be looking in. So what I'm going to do is say, instead of calling that one k plus 1 and that k, we're going to say the right one is going to be k, because then that ends us perfectly on B. So what number would be right before k? K minus 1, yeah. So we just have to shift to the left to make that happen. So that's going to be x sub k minus 1, then f of x sub k. And then I can let my sum go from 1 to n. Just to double check that that's true, if k is 1 up here, k minus 1 would be 0, which means take the left height and then the right height to find your trapezoid there. So that makes the first one correct. And then if we double check, what's the last one look like? The last one would have an n minus 1, which puts me here, and an n, which puts me there, and that would find the last trapezoid. So that looks like I set it up right now. So this is what we call the formula for the trapezoidal rule. Now, something interesting happens if you write these guys out. So I'm going to simplify the notation just a little bit and make a note that I could say f of x1 is just, we can just call that y1. And so, for example, f of x sub k, that would just be the kth y value. So there's just a little less stuff to write down. If I do this for 4 subintervals like the previous problem, then what I'm going to have is I have that h over 2, or h over n. So let's say n is equal to 4. Every single one of them is going to have this same h over 2 in it. So I'm just going to pull that out because that's constant. So I have my h over 2 here. And then the first one says take y value 0 all the way at the left and add it to y value 1. So that's the first average height. And then the next one, jumping through the interval, would be y1 plus y2. And the next one would be y2 plus y3. And the fourth one would be y3 plus y4. So just double checking that, thinking about the number line. Let's draw the number line down here. So this would be x0. That would be x sub 4 at the end of my interval from A to B. X sub 1, x sub 2, and x sub 3. All right, so x1 to x0 leads me to y0 and y1. So there's my first trapezoid. My next trapezoid says, hey, you got to plug in the left-hand endpoint, so you need to plug in x1 again and get y1, and then you'll get y2 here. So notice that these middle guys get reused more than once. So if I clean up this sum right here, what's going to happen is we still have that h over 2 hanging out front. y0 only appears once here. It only gets used once. But notice that y2 gets used for both of these trapezoids, here and there. So I end up with 2 y1s. And then how many y2s do I get? I'm going to get 2 of them because it has to be used twice because it has 2 adjoining trapezoids. So there's going to be 2 y2s. Similarly, there's going to be 2 y3s. So any partition that's in the middle somewhere, not on the edges, has to be used twice. But the ones on the edge only get to be used once because we ran out of trapezoids on either side. So it's kind of interesting. There's 2 different ways to look at the formula. One way is the summation that I showed earlier. The other way is you're always going to have an h over 2 multiplied by everything. The first and last y values only get used once, but every y value in between gets used twice, which is kind of cool. So for small values of n, you don't need to mess with summation notation, which can get, kind of kind of scary sometimes. You can just calculate the y values and singly use those and doubly use all the ones in the middle, and you have your answer. Yeah, if you distributed that 1/2 through, yeah, you could say you use all of y1, 2, and 3 and only half of y0 and y4. That would be definitely another way to look at it. Yeah. So what Clinton said is distribute that 1/2 through, leave the h out here. We would have half of y0, and y1, y2, and y3 only need to be used once each. And we would have half of y4, yeah. So that'd definitely be another perspective on the sum, which is kind of cool. All right, so let's calculate the trapezoidal rule for the problem we were just working on. So, new page, we have f of x is equal to x squared plus 5 on the interval from 5 to 7, oops, including 7, and we are letting n equal 4. And we want to see what the trapezoidal rule gives us. And so I'll write it as a summation in a little bit. I'm gonna use that second way I showed a minute ago. H in this case is the width of the interval, so 7 minus 5, divided by the number of subintervals. So like our right-hand endpoint rule, we still get the same H. That's not changing because we're having the same subinterval size as we move through. So H is still 1/2. The formula says take H over 2 times each of the y values, sort of. And so H over 2, 1/2 divided by 2 would be a 1/4. So I'm trying to approximate the area now. So I'm gonna have 1/4 times, and using this formula right there, I just pick the first, the 0th y value. Back page, no, forward page, there we go. So plugging in 5, so I'm gonna have a 5 squared plus 5, that's y0, plus 2 times y1, and remember how we jumped through by half, so y1 is gonna be 5.5, so I'm just gonna call it 5.5 squared plus 5, plus 2 times y2, which was 6, plus 2 times y3, which is 6.5 squared plus 5. And then finally, the last one doesn't get doubled. It's just 7 squared plus 5, because that's the endpoint. So notice when we plug in the endpoints, those don't get doubled. Everything in between gets doubled. And so let's type that into a computer and see what we get. Let's see, where's my computer? Let's bring that over here so you can see what we're typing. All right, so this is similar to that. I want that to be a 4th. And then I need parentheses. And what am I missing? Oh, I'm missing that one. All right, there's my left, there's that one. Okay, so if I typed it correctly, I get 82.75. Okay, so I'll bring my screen back that I typed it into. So I was trying to be very careful with parentheses, 2 times y2, 2 times y, oh, let's see, that's y1, this is y2, this is y3, and there's y4. And Google added even more parentheses trying to clean it up. Go away. Huh, I won't go away. So 82.75 is what I'm getting here, which should have less error than the right-hand endpoint. So 82.75. I don't know if I wrote down that last one. Where was that? Back further. I did not. So 88.75. Okay, so this one was about 88.75. There's a way to estimate the error. Now, in this case, I actually know the real answer because I can find the antiderivative. So this is more useful for functions I can't find the antiderivative. Okay, so we'll try it on a function we don't know the antiderivative of shortly. Let's try another one. So that's the trapezoidal rule. And again, there's two ways to look at it. One way is by just considering it's always going to be h over 2 times your y values where the endpoints are single and the interiors are doubled. Or you can use the Riemann sum version up here. So I'm going to write down the Riemann sum version next, and then we'll do another one. So to do the Riemann sum, I have to be able to describe each x value. So let me try to do that. New page here. So I'm sticking with the same exact problem, I'm just going to write it down different. F of x equals x squared plus 5 on the interval from 5 to 7, n equals 4. So h, remember, is the width, which is 2 divided by n. So in this case, 2 over 4 or 1/2 is what I'm jumping through by. I'm starting at 5. And so either I draw the number line to try and figure this out, or I make a table to try and figure out what's going on. So this one right here, I got to get from 5 to 7. As far as my counter k goes, here k is 0, and here k is 4. And then I need to jump through here by h. Oops, h. So I keep from 5, I add h, then I add another h, then I add another h to move through. So this first point right there, that would be x sub 1, right? That's going to be 5 plus whatever h is. And this second one here, that would be x sub 2, right? Wouldn't that be 5 plus 2 h's? And then what would the third one be? 5 plus 3 h's, yeah. So that turns out it's pretty straightforward when the interval is the same width. H happens to be 1/2. Okay. So with k as my counter, I think that x sub k starts at 5 and then adds on k h's. Because k is my counter, k is 1, k is 2, 1h, 2h. So I'm trying to find a correlation between my counter and what I end up with the h's and the starting point. Okay. And a lot of problems we did before, we started our interval instead of at something like 5, we started at 0. So we didn't have that plus. It was usually something like k times whatever h was. Okay. But here, because we're not starting at 0, we have that start at 5. So now I know what x value I'm plugging in. So I can use the Riemann sum version of the formula. The Riemann sum version says you want the sum as k goes from 1 to n of h over 2 times parentheses f of x sub k minus 1 plus f of x sub k is what we determined. And for this particular situation, I know two things. I know h is going to be 1/2, and I know that x sub k is 5 plus k times 1/2, right? 5 plus kh. And I also know that f is x squared plus 5. So I'm going to try and write this in a Riemann sum and then type it into a program that can do sums for me. Because it's not too bad to do it by hand when there's 4 subintervals, but what if there were 10 or 100? Don't want to write that down each one at a time. That gets a little crazy. So let's see, we're going to have the sum as k goes from 1 to 4 of 1/2 divided by 2, so that's our 1/4, times parentheses, and this is the formula that's really important. First, we plug in k minus 1 in there for the x value. So my x value, I'm going to stick in parentheses. I'm going to switch to a different color. So my x value is 5 plus, and here I got to use k minus 1, so parentheses are important. And I need to square that x value and add 5. So I've just calculated the first y value. And now I need to calculate the second. And the second says plug in your x value, which is just k for the second part. So that's going to be 5, parentheses for my x value, 5 plus k times 1/2 squared plus 5. So it's a little more complicated because I have to plug in the x value to the function in 2 different ways. And so again, this is my function, x squared plus 5. And here it is again, x squared plus 5. First time, it's x sub k minus 1, so I had to adjust. Second time, it's just x sub k. So notice the only difference really from here to here is there's a k minus 1 in parentheses. There's just a k. But now for n equals 4, this is like super overkill. But if somebody said n was 10, do we really want to do this? That would be 11 endpoints to plug in, right? Because we have the 0th one. Or if somebody said n was 100, do you really want to do that 101 times? I don't think so. Right, so then we need a summation program to do this for us. So Desmos, I believe, does sums. Geogebra does sums. Take your pick. I think I'm going to use Geogebra since I already opened it. And let's hope Geogebra behaves today. It wasn't behaving for me the other day. So I want to do, I think I just typed sum. And it says sum wants a list. Oh, okay, so sum won't work directly. I think maybe I need sequence. Aha. Okay, so for Geogebra, and who has a TI here? TI behaves the same way. In order to do a sum, you have to sum up a sequence. And that's in the list menus on your TI. So I don't have a TI on me, but I believe if you go to the list menu, let me look over your shoulder here. Oh, maybe, oh, the new TIs just do it. Okay. All right, sorry, I'm thinking of old TIs. Apparently I'm out of date with my TI technology. Yeah, so TI does have a sigma notation summation. Does yours have one, Ventura? Did you look? Did you go to the list menu? I think that's where it is, right? Math, maybe? Okay, you have an older one. So you would have to do sum, and then further down is sequence, I think. Or is it in a different spot? There's sum, and then we need to find sequence. So go back to, I think it's still in list. And how about ops? Then list, the middle one, and then you can grab sequence there. Okay, yeah, and then it wants, so it's kind of similar to Geogebra. It wants to know what is the function you're trying to make a sequence out of. So for me, it's going to be this whole thing is my function that I'm trying to sequence, my expression. So I have to plug that in, and the TIs ask what variable you're using. I can't remember what Geogebra asks for. Let's see, if I start typing here, I have my 1/4. It's not being helpful here, times parentheses. And then here I have to be careful. Let's see what was next. Another parentheses, and then it was 5 plus parentheses k minus 1. And you could use an x as your variable there, so you could type x minus 1. And then I want to square. Oh, it's not quite right. It's not showing my cursor. Divide by 2. There we go. K minus 1 over 2 plus 5 squared. Oops, wrong spot. Plus 5. Put that in the right spot. X squared plus 5, where x is 5 plus k minus 1 over 2. That looks right. And then I want to add that to parentheses 5 plus k over 2, my x value, squared, oops, wrong place. Square goes out here. It's the right place now. And then I want to add 5 to that. X squared plus 5 for k minus 1, x squared plus 5 for k, and that's all multiplied by 1/4. I think I typed that right. Let's see. Yep, that looks right. Okay, so that's the thing I'm adding up. And if I go over here and then do a comma, what does it want next? My variable, maybe? Starting at 1 and going up to 4. And then it says 82.75. Is that what we found before when we did this by hand? Okay. Were you able to do that on the TIs and get the same thing? So the nice thing about doing it this way is if somebody says, well, I need 10 subintervals now, all I have to do is replace the n parts with a 10. And so if I look back at my notes here, n appears in the h, and it appears at the top. And that's it. That's the only time I need n, right? Am I lying or am I telling the truth? This is k, h. Let's see, I gotta go back a step. Where's my general formula? Oops, where'd it go? Let's see, I gotta double check I'm not lying there. Something doesn't sound right about what I just said. I think you're right, that's what I was thinking too. So let's see, if I switch colors, h is equal to, in this case, the width for this one is always 2, but it's divided by n. And this is always kh here, yeah. So that will change there. That'll be 2 over whatever n happens to be. So then if I do change n, I have to change it here, 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 and there. Okay, so I have more than one place to change it. Geogebra actually offers me a shortcut for that. Sort of, because when I enter a function into Geogebra, it calls it f, and then I can just reuse it that way, which is slightly less stuff to type. So for example, in Geogebra ahead of time, I could have said, take the function x squared plus 5. What happened? Why isn't it typing? There we go. X squared, there we go, plus 5. And once I enter it, it says your f. So up here, I could just say f of this number, f of that number. So for a complicated function, it's worth my while to do that. And sometimes it's not a bad idea to separate the sequence from the sum. So let's see if Geogebra behaves better. So if here I go sequence, expression variable start end, the TI offers an optional increment usually too, like do you want to jump by 1 or 2 or 4, which can be helpful. Usually I like incrementing by 1. And so then I can say my expression, let's say I let n equal 10 here. So it would be 2 over 10 times parentheses f of, ooh, it put it at the end. It was doing this crazy thing to me the other day. It was putting stuff in the wrong spots. I bet, let's see, what is GeoGebra built on? Is it Java? No, it's built on Flash. I'm gonna have to update Flash to make it behave right. F of, there we go. Close parent, did it again at the end. Okay, GeoGebra is misbehaving. Hopefully it behaves well for you. See if I can edit it up here. So editing it up here, I would replace the 1/4 with a 2/10 and not worry about simplifying it. And then this 1/2 right here, I think I would want to rewrite that in parentheses. Oops, didn't like that. Around the k and multiplying it by, it's getting multiplied by just h, right? 2/10. Oops, I made a mistake then. Because this should be half of h right here. So that should be 1/2 times 2/10, half of h. All right, and then over here, I would want to clean this up to be, I guess I could write it as 2k/10, and then do it 10 times. 1/2 of h, 5 plus k minus 1 h, 5 plus kh. I think that looks right. So if I hit enter, GeoGebra says a better estimate is 82.68. So let's just, oh, we are out of time. Darn. Let's check this real quick. So we are trying to estimate the integral from 5 to 7 of x squared plus 5 dx. So let's see how close the trapezoidal rule came. So we know an antiderivative for this is x cubed over 3 plus 5x from 5 to 7. So that's going to give me 7 cubed over 3 plus 5 times 7 minus 5 cubed over 3 plus 5 times 5. And I'd rather not do that in my head today. Asking my calculator what it thinks about that. Let's see, Google Calculator, 7 cubed over 3 plus 5 times 7, oops, minus parentheses 5 cubed over 3 plus 5 times 5. And Google says, ooh, it didn't like the way I typed that. It will not calculate it. Oh, I see I missed a cube there. Google says it's 82.666666. Does that sound good? And so let's double check what our previous ones were. The 10 trapezoids was, oh, let me bring this in. Yeah, so here's my 82.6666. 10 trapezoids gave me 82.68. That's not bad. Took me 10 trapezoids to get 1 decimal of accuracy. I'm off by about 100th. When we did 4 trapezoids, we were off by what? Where's that one? 82.75. So we were off by about 1/10-ish. When we did the right-hand endpoint, though, we were way over, right? So the trapezoid with same number of intervals as the right endpoint is way, way, way more accurate, right? So here's what we're going to do next, and this is super exciting. Wait till you see this tomorrow. Ah, tomorrow isn't until Monday. Darn it. So sad I was sick yesterday. We have to wait till Monday for this super awesome next thing. So you actually don't have enough information to do the homework, but maybe I'll record a little video tonight or tomorrow for this. With our curve like this, right, we're finding these trapezoids, and so we have this error, right, coming through like that. What we're going to do instead is, given a few points, if you know 3 points of a curve, then you can calculate a parabola through those 3 points. So what we're going to do is, instead of looking at one column at a time, we're going to look at 2 columns at a time, and we're going to find a parabola through each of those 2 columns. So if my next set of points were, say, over here, right there, I would have columns like that. I will find then a parabola through those 3 points there. And so the cool thing about this is, not only, like, this is kind of like a tangent line approximation. We're going to do what are called parabolic approximations of the curve, which means we get to match the curvature. So we're going to get rid of even more error. And this is called Simpson's rule. Okay, but it's a little trickier because we have to be able to calculate these parabolas, and instead of going 1 at a time, we have to jump through our intervals 2 intervals at a time. Okay, so it's a little crazier, but it's not that bad once you do it a couple of times. So I'm sorry we didn't get that today. The problem with the homework is each problem says do the trapezoidal rule and Simpson's rule, which, oh, I'm sorry about that. I will record a little video tonight or tomorrow for this so that you can do some over the weekend. Yeah, the trapezoidal rule is rough for the first couple tries, but then it's not so bad. When it's just one step more complicated than the trapezoids, really. Simpson's rule, that is.